education. This year, our symposium is devoted to game theory and game theoretical semantics. I'll be very brief, and first of all, I would like to thank you for your coming, and I hope not too many of you are struggling with jet lag, but still, thanks a lot for coming. And well, thanks a lot to the University of Latvia for supporting our symposium and our activities. I wish you a great conference, lots of discussion, lots of inspiration and great ideas in the next 3 days. And now I'm honored to give the floor to the University Rector, Professor Mats Auziņš.
Dear colleagues, dear guests, I'm very happy and honored to welcome all of you to the University of Latvia, to small aula of University of Latvia on the occasion of opening your conference about game theory and game semantics. It's happening in small aula of the University of Latvia, although we call it small aula. Actually, it's a very important hall for our university because now already 93 years ago, University of Latvia was established exactly in this room. At that time, it was the only aula of the university. Now we have the large aula as well, but this still is a very important place for us with a lot of historical artifacts. For example, this podium from which I am speaking is designed by one of our first rectors, Agent Slaube. He was architect by training, and he designed this hall, including this podium from which today all the talks will be presented. For those of you who are for the first time at our university, I can give you a very brief introduction to our university. We are the largest university in our country and the only one classical type university, which means that we have almost all subject areas. When I'm saying almost all, we have very little of engineering, because we have a Riga Technical University, which is mainly for engineering. Otherwise, we have social sciences, humanities, medical science, teachers training. All fields are covered at our university. We are not very large university for European scale. We have around 18,000 students. But for Latvia, it's really large university, because if I'm willing to impress my guests, I'm always saying, look, it's almost 1% of current population of Latvia. And that's true. Probably it tells something about university as well. It tells something about country. Country is small. But it's reality. It's almost 1% of current population are students at this moment of this university. It was established, as I said, 93 years ago. Again, not a very old university for European scale, but again, I must say that it cannot be older than that, because it was established exactly a couple of months after the country was established. It was established as a national university and national research center. And still we are the leading research center in our country. It's always hard to count research output, but you can measure that, for example, in science very easy by number of publications in Science Citation Index journals. And if we are counting science in this way, then it appears that more than 50% of all the research output which is coming in this country is coming from this university, of course, together with our research institutes. If we are counting number of defended PhD theses, again, more than half of all the PhD theses defended in Latvia are defended in this university. I think this gives you some impression what kind of university we are. Now coming back to your conference. As you can imagine, rector of the university is opening very many conferences during the year. But when I'm coming to the conferences organized by Professor Schilters, I'm always very much impressed. Because even if the number of participants is not huge, I always have a feeling, and that's true, that the best experts in the field are gathered in these conferences, that discussions are highest possible level and very professional. Another aspect which is always very appealing for me is that these conferences always start with some public lecture. Some lecture which is understandable for everybody, and actually, honestly speaking, I'm looking very much forward for this year's open lecture and public lecture, because think that I will be able to learn something for myself personally as well. So I wish the success to your conference. Many interesting and stimulating talks, as well as I hope that you will have enough time for informal interaction. Because as we all know, for conferences, formal talks are very important, but this informal part is equally important, because during this part of the conferences, sometimes new contacts are starting, maybe new projects are developed, and I hope very much that this part of conference will be very active as well. Finally, I hope that our Baltic Spring, for which you never know what kind of weather you can expect in a couple of hours, that it will be favorable for this conference as well. And actually in weather forecast we have good news that it will be warmer and the weather will be nice, because hopefully you already noticed that we have beautiful city Riga. I hope that you will have time to enjoy city as well. So all success to your conference. Thank you.
Thank you so much, Professor Olzinch, for your kind introductory words. Well, and now it's my great pleasure to introduce our keynote talk by Professor Gabriela Sandu. Professor Sandu is one of the most prominent contemporary logicians working on game theory. Together with Jaakko Hintikka, he's one of the founders of the perhaps most influential conception of game theory in contemporary logic and philosophy. He's published widely on topics in game theory, formal semantics, mathematical logic. Gabriela Sandu has been professor at the University of Sorbonne, Paris, and is currently professor at the University of Helsinki. It's my great honor to give the floor to Professor Sandu, and the title of his talk is Games and Signaling in IF Logic.
Well, thank you. Thank you very much for this honor and this opportunity to be here in this monumental university and in this beautiful city. And I think it's also a very good idea to bring together researchers working on these combined themes, which is games and logic. This as games, logic, game semantics. This is a new research paradigm which has crystallized in the last 20 years or so around researchers in computer science, logic, game theory, philosophy, linguistics. I am, which is very active nowadays, and well, just which can be also seen perhaps from the number of publications, just to quote a few of them, which have appeared in recent years, and these are just a few of the books which have come out, and several of the participants are here in this audience, either as organizers or as speakers. So this is the. I am myself a philosopher, and so I'm going to tell you a few basic things, elementary things concerning the basis and the foundations of games and logic, which of course doesn't mean that these are going to be easy or so. I am borrowing a distinction which is made by Van Bentham in one of the books I mentioned, but it's a book which is forthcoming now, which is called Logic in Games. And he makes a distinction between logic of games and logic as games, and the logic of games, which has been also one of these exploding research trends recently. I mean, scrutinizes games by using modern logic. Actually, it takes basic notions which are used in classical game theory and analyzes them using tools, systematic tools in modern logical systems. For instance, preferences in game theory are analyzed logically using preference logic, or games and strategies are used using dynamic logic and its variations, or then various notions of knowledge and beliefs. They are modeled, they are studied using dynamic epistemic logic. I'm sure you'll hear a lot about these things from the talks which will be forthcoming, by the talk by Alexandru and Sonia and others. The other games is logic as games. The other sort of side of this combination, which is mentioned by Van Bentham, is logic as games, and that is, well, logic as game. You look at traditional notions which are used in logic, and then you recast them in game theoretical form. This is something which has been going on for half a century or so. And for instance, we take traditional logical notions like truth, material truth, and then we recast it in terms of evaluation games. This is game theoretical semantics. This is an area where I have had the chance to work myself with Jaakko Hintikka, one of my teachers. Or you take notions like proofs and arguments, and then they can be recast as tableau games or dialogical games. And I'm sure also you'll hear something about this from the talks of Helge Ruckert and perhaps Professor Japaridze. Or then you can take linguistic conventions. They are supposed to give you an analysis of meaning, linguistic meaning, and linguistic conventions, and they have been modeled since the times of David Lewis by signaling games. Or then you take a more mathematical notions like elementary equivalence between models, and we say, I mean, just one, two sentences, one, two models, I mean, satisfy the same sentences, and then you characterize this as in terms of model comparison games. Myself, as I said, I'll just place myself in this evaluation games tradition, and I apologize to those who have heard parts of my talks, but only parts before. So, I mean, Hintikka had this idea to characterize, I mean, material truth and falsity, and I mean, by semantical games or evaluation games, and this is GTC, is game theoretical semantics. You analyze the logical skeleton of a sentence, and logic is the driving force here, and so at the end you are supposed to characterize, to define when a sentence is true or when it is false, and this is done once again via semantical games. But of course, this presupposes that some of the basic items, lexical items, their meaning has been fixed and has been settled. And so the question is how to account for the linguistic conventions that settle the meanings of these basic terms. And so once again, I mean, we have this idea of logic, that you have some basic lexical items, you have some logical operator, you have complex sentences. The game theoretical part is going to give you give a game theoretical interpretation of these logical operators here, but then the question is, how do you settle the meaning of these basic lexical items? And there it's where the signaling games of David Lewis, in a famous book for philosopher convention, what it does, And Louis' work on convention is based on Schelling's work, and this is a very interactive idea with game theory nowadays, deep connections with the people in Amsterdam and elsewhere, with games by Parikh, Decker, Van Rooij, yes, so I repeat myself, they are supposed to tell you how meaning conventions arise. And but then again, I borrow something from Johann van Bentham. After you have settled the meaning of the basic lexical item, then you have settled the notion of truth and falsity and the meaning of logical item, then just the game of conversation, so to say, just starts. You have to convey informations to try to persuade others, and this is a real contribution of one of the real contributions of the Dutch logic, where dynamic epistemic logic, so for analyzing updates, exchange of information, belief revisions, questions, etc. The overall purpose of all this is to arrive at a sort of integrating, unify logic of scientific, of rational inquiry. So again, I come back to my main purpose of the talk is the evaluation games, so the games, game theoretical semantics, semantical games. Historical motivation, very shortly, I think this is perhaps the best motivation that we have in terms of history. We look at quantifiers and connections. You have a sentence there, you have different logical operators, then one of the best way, they depend on each other's. I mean, games are very good to analyze that. As Goldfarb, in a famous paper, Logic in the 20th, the nature of a quantifier, as he points out, I mean, the connections between quantifiers and choice functions, or more precisely between quantifier dependence and choice function, is the heart of how classical logicians in the 20th view the nature of quantification. Well, for a more systematic point of view, and I'm grateful to Ahti Pietarinen for pointing this out, we can look at one of the Fields medalist, Terence Tao. I mean, what he tells us is, well, we try to, in logic, we try to express basic dependencies and independencies between different magnitudes. For instance, try to say that for every x, there is the y depending only on x, such that b, xy, this b is just a relation between two, and it's true. We express that in this way. For all x, there is a y, bxn. We regiment it like that. Or for every x, there is a y independent of x, such that b holds, the relation b holds between x and y. We express it like that, putting the existential quantifier x. There is a y for all x, b, x, y. But then things are getting more and more complicated, as Tao observes. When we have 4 quantifiers, for every x and x prime, there is the y depending only on x, and the y prime depending on x, and x prime, such that q, x, x prime, y, y prime holds. As you see, we had to rearrange the quantifier in such a way that, well, here we have y depending on x, but then y prime depends both on this, both on x and on x prime. Well, actually it depends also on y, but y depends on x, so this doesn't matter actually. So that Hintikka thought about this in the 70s. He's not actually the first one. The first one, to my knowledge, was done in a systematic way is Henkin, but Hintikka also extended this to connections and negation. He said, well, why don't we interpret such a sequence of quantifiers by semantical games? A semantical plays that we play with a sentence, A, and then we have in a certain situation, and this situation is just a model M, and then we have an assignment, a particular value, so the assignment assigns values to the free variables of the sentence. And so the game is played by 2 players, the existential player, or Eloise, and then the universal player, or Abelard. And so the existential player tries to show that the sentence is true in that particular situation, M, and the universal player tries to show that it is false in M. And so at the beginning, these two players, they have two roles. One is a verifier, actually, as I said, tries to verify the sentence, but we mark this explicitly. This is a verifying player, and then the other one is a falsifying player. It tries to falsify the sentence. And these are the rules of the game, so it's very simple. We have them on this page, all of them. Well, you can imagine you start with a sentence from outside, then if the player meets a universal quantifier, then the universal player chooses an individual for all x. And then they move to the next step. I mean, the structure of the sentence tells them the order of the moves. Then an existential player, then the existential player, the verifier will go to the negation is tricky, and that's I think the insight that the game theoretical semantics brings into play. Just the role, the two players, Eloise and Abelard, change roles. One is going to become the verifier and the other one the falsifier, and vice versa. And then conjunction is a move by the falsifier, disjunction is a move by the verifier, and finally we reach an atomic formula where there are no logical operators any longer, there are no moves to play. Then the two players just sit back and contemplate the result. If the atomic formula is sort of true in that situation, particular situation relative to the assignment, just to its free variables, then the verifier, the player who is the verifier has won. If not, the player who is the falsifier has won. So this is, but then the important notion, because that's what games brings in, is the notion of strategies. So again, this is a technical notion. It's just a method. It's just a method. I am thinking of strategies as deterministic functions, which is going to tell you to each player, I mean, in every possible position where he is going to find himself or herself, he's going to tell you what is the right choice to move. So the players do not play blindly, but they follow a strategy. And then we have this crucial definition. A definition defines truth and falsity. So a sentence A is true in a situation, a relative certain sign, if and only if there is a free strategy for the existential player in the game, and if it is false, if there is only strategy for the falsifying player for the universal player for our result in the same game. And then we have a result in game theory, which is well known. It's for this kind of games, which says that in every game, either the existential player has a unique strategy, or the universal player has a unique strategy. So we have sort of our first encounter between logic and games. The principle of bivalence is for every sentence, either the sentence is true in a situation or is false, is now equivalent to a game theoretical principle, which is the basic result in game theory for a certain class of games, which is Zermelo theorem, which is a determinacy of games. Well, I'm not going to bother you so much with the details. I just so that for those who haven't seen that before, it's very good to see an example of a game. For instance, suppose you play a game with the formula for all x there is a y, x equals y. For all x there is a y, x equals y, and the situation in which you play the game contains two elements, 1 and 2. Any play of this game will have a very simple form. The universal player, for the universal quantifier for all x, will have to choose an element A. The existential player will have to choose an element B, and then the game ends with the atomic formula x equals y. If the two elements are equal, then the existential player wins, otherwise the universal player wins. So a strategy for the existential player, of course, in this case will be the identity function for every x for every A chosen by the universal quantifier, it has to produce an element which is identical to X, so this is the function f, which is an identity. And well, Abelard's strategy, Abelard's proposed to falsify the sentence, and so he doesn't have a winning strategy, of course, because he cannot choose as a value for X an element which is winning against any possible choice of his opponent, Eloise. There is no winning strategy for Abelard, and we knew this already from Zermelo's theorem. Why do we want to use games here? What is the advantage of using games? Well, one of the advantages is that if we look at plenty of our logical principles, especially the ones which are formulated in terms of equivalences, for instance, commutativity, A and B is equivalent to B and A, or associativity laws, like the one I mentioned here, or the absorption laws, or distributions laws, which are just elementary logical principles that we study, that we encounter in the logical textbook, then they perhaps look like proofs. So sort of more proof-minded logicians say, well, let me just build up a proof in natural deduction style or in a sequence calculus. But actually, the game theoretical perspective in this case, they are just recipes. They are just recipes for converting one strategy into another. I mean, in all the underlying situations, in all the underlying models. Well, that's very easy to see. I mean, if you look at any of those, I mean, you can well, suppose you look at this one. Suppose that this one on the left is true. Well, just mean that A or A and C. Well, it just means that the existential pair has a winning strategy here. Well, what is a winning strategy? I mean, this junction, the existential pair has to choose at this junction. And if she chooses this, and she wins this, of course, then she chooses that. If she chooses that, so she has to win this one. But she has to win this one, it means that she has to win, of course, against any possible rules of her opponent, conjunction. We'll have to move either this or that, because that's a natural conjunction, so she would have to choose that. The same thing is if we look at other logical laws like double negations or De Morgan laws. I mean, if we look at double negation, just negation in the logic just means switch rows. So, of course, if the player switch rows and then they win A, then they are back to the initial situation. Of course, they can win A and vice versa. So all these laws, as I said here, are statements about which player is the verifier and whose turn is to move. And the same observation about negation and the movement of negations to the quantifiers. And all right. So this is one of the advantages of using games. But then another advantage of using games is, again, I go back to the observation by Terence Tao, and then he said, well, but then one cannot always express sort of more complex relation of dependence and independence between quantifiers. So think about one like that. For every x and x prime, there is a y which depends only on x, and a y primes which depends only on x prime, such that the relation holds. So that is very tricky. Force quantifier, just can you imagine? I mean, we want to see the existential quantifier which depends on one universal quantifier. And then you have the second existential quantifier which depends on the second universal quantifier, and that's all. So you want to save this kind of parallel sort of dependence relation. And as Tao himself put it, he said, it seems to me that first of the logic is limited by the linear nature of its sentences And every new variable that it introduced must be allowed to depend on all the previous variables introduced to the left of that variable. This does not fully capture all the dependency trees of variables which one deals in mathematics. So of course this is a sort of Terence Tao, it's called provoking Derrida, who said that the linearity of the linear order, I mean, it's basic, it's sort of basic, you know, thinking, but no, Tao didn't write it with that purpose. But that is the basic observation that many other logicians have made before him. I'm just quoting him here just for an illustration. And so how are we going to solve that? And again, games help you to do that. There are two solutions to such things. I mean, you want to express sort of dependence of your logical operators, dependence and independence, which cannot be expressed in a linear, sort of traditional first-order notation. And these two logical systems, one of them is the one which I developed with Simpozija, and there's been many other contributors. Or some of them are here, for instance, and that is going to express it in a new notation. Well, for all x prime, and then we want to say that there is a y which depends only on x. But if it depends only on x, we just exclude x prime. That's the way to say that. So there is a y which is independent of x prime. Well, we also have to say that there is a y prime which depends only on x prime. There is a y prime which depends only on x prime. We want to exclude the other one, x and y. And then we come up with this formula. And the interpretation that we give to this kind of signals quantifiers is semantical games of imperfect information. And they have two consequences. Actually, there are many consequences, or several consequences, but I just single out two of them. Indeterminacy, there are sentences which are neither true nor false. And then they have a device which is called signaling, which has been discussed, and which is something I want to say more here. And the other two logical solution, which has been developed in the last 10 years, or actually in the last 5-6 years, it's called the system which is called dependence logic, which is by my colleague in Helsinki, Jouko Väänänen. So we give an alternative formulation, and the alternative formulation was, instead of saying actually that there is a y independent of x prime, and there is a y prime which is independent of x and y, why don't we actually say, why just don't we spell out the dependence relation? So we use just the classical quantifiers for the x prime, there is y, there is y prime, and then we have y depends only on x, as tau 1 did. And then we say that y prime depends only on x prime. We say here, this is a new logical constant, the equality here. And then finally we say that extend up in this relation. And the interpretation which has been suggested by Ludwig Hodges is that, well, actually we interpret it by compositional methods, with generalized Tarski type definitions. So two logical systems, perhaps they give a flavor of what is the difference between a kind of game theoretical approach and the compositional approach in logic. In the game theoretical approach, then you use these sort of games to interpret sentences, and then you use strategies, the existence of strategies, to try truth or falsity. In the compositional kind of interpretation, you see try to eliminate games, and then you go for a Tarski type composition interpretation. And so actually you go for that because, in my opinion, you don't want to have signaling in the logic. So let me say something about the notion of signaling. because everything that I'm going to say after that is more or less to be sort of variations of this theme. So you have a first example like, for all x there is a y which is independent of x. So just imagine, I mean, the universal player has to choose an individual. The existential player has to choose another individual without seeing the choice made by the universal player, but in such a way that they are equal. This is a game which is, in classical game theory, is known as matching pennies. So, of course, none of the player has a winning strategy. I mean, I just by mistake, the existential player can choose the same individual as the universal player, but he doesn't have a systematic way, a winning strategy to do that. So, that sentence, for all x there is a y, independent of x, the first sentence, is false. We exclude models with one element. All the models have at least two elements. But then, as Spoljic has pointed out, then just by inserting the atomic quantifier, there is a z in between the two, you transform a logically false sentence in a logically true one. So, why is that so? The signale is usually known in game theory as a kind of moves by the player where they indicate to their partners, I mean, the position where they are, the kind of information they hold. And this is, so in this system, of course, it's, I mean, this is the example shows that, well, of course, for all x there is a red, the existential player now sees the choice. But even if he doesn't see here there is a y, and maybe this is x not x prime, this is misprint. So even if he doesn't see x, but he sees his partner, so to say, existential, the other existential player's move, and he can copy. So that he can identify why they need to left. So this is perhaps the difference between the first sentence is equivalent to there is a y, truth equivalent, there is a y for all x is identical to y, and the second sentence which said that in strategy, thinking about strategies, quantifying existential strategies, there is a f, there is a g. This is a strategy that for all x equals f of g of x. So I can, the first function just, one of the functions give you the value of x, and the other function again, I can, it's also the identity function. I can identify the, so the, but if you are not, if you don't go for this notation, and then you go for something where you mark, this is the dependencies in logic, well, the first sentence would just be given a correlate is y, and then this y is this is just, this is the first comment that the y is independent of all the, doesn't depend on anything, so it's a constant. And then you have x equals y. But the second formalization of the term of dependencies is for all x is the z is the y, then y depends on x, because the y depends on x, but then on that, and then x equals y. You see, again, the difference between a game theoretical interpretation and the composition interpretation, because in a composition interpretation, you have to start from the bottom. I mean, if you start from the bottom here, you just start with an interpretation of x equals y, you are going to be surprised at some stage later on. That's why it proves to be very difficult for a composition interpretation. You are going to be surprised later on that you just encounter the z that you don't have here. And while if you go for a composition interpretation, then you go for the dependent logic, then you have to have all the elements that you encounter later, you have to have it in the atomic formulas, and that's why then you go from that. I just emphasize this example because it gives me an opportunity to say, well, if you like the style of all logic compositional semantics, then you have to go for certain interpretation, certain representation logic. If you go for the game theory interpretation, then you go for the other notation, for the other representation. Well, I am not, I skip over some of the examples. I mean, how dependency in the game theory interpretation relates to uniformity a term of uniformity in some of the mathematical examples. But then I spoke already about signaling in higher logic, this basic variation. I'm going to say a few things which are just variation of this kind of logic formulas. Look, once again, at this triple variables. For all x, there is a y, there is a z, there is a y, which doesn't see x. Say that x equals y. You can identify y, can identify x, even if it doesn't see, just because there is a z in between. Well, you have the same pattern in a sentence defining the infinity, Dedekind infinity. It's a sentence for all x, there is a y, saying that there is a z, doesn't see x, so z managed to identify y, even if it doesn't see. There is one extra condition which just is crucial, and this sentence is true in a particular situation, in a particular structure, if and only if the structure is infinite, which is Dedekind infinite, a particular mathematical notion. Otherwise, this sentence defining infinity is indeterminate on all the finite structures, all the finite situations. Then I move to another application of the same phenomenon, signaling, which is in terms of lawyers, signaling games. So these are communicative situations where you have a communicator C and an audience A. So we have a kind of sender of a message and the receiver A. C observes one of the several states in which she tries to communicate or signal to I. So the communicator in a certain situation, then he is going to send a signal to the audience. The audience doesn't see the situation he is in, and the communicator tries to signal him that he is in this particular situation. After receiving the signal A, the audience performs one of several alternative actions which are called responses. And every situation M from which a signal is sent is correlated somehow with the best response. We know that before. We're going to see an example. And Lewis argues that the word acquires its meaning in virtue of its role in the solution of various signaling problems. So if the two players, actually, if there is a kind of, or perhaps I move to the, so once again, a kind of more logical modeling of this same setting is that while you have a set of situations or states of affairs, and then you have a set sigma of signals, and then simply a set R of responses. This is how logicians model this kind of situation. And then when we send a signal, this is usually in logic encoded by a function, which for every situation measures what is the signal which is going to be sent from it. We just assume that for every situation there is a signal. And so it's called an encoding function, which every situation gives us a signal which is going to be sent, and then a decoding function, G, which for every signal you have to think of the audience, of the receiver. From every signal he receives the signal, and then he has to decode it somehow to perform the best action. To decide which action to perform in response to the signal he receives. And the signaling system is just a pair FG of encoding and decoding functions, such that their composition, mathematically speaking, then give you the best action. So the signaling convention, this is classical. A driver is trying to back into a parking space. She has an assistant who gets out of the car and stands in a location where she can simultaneously see how much space there is behind the car. There are two states the assistant wishes to communicate. It's just the signals at her disposal. Just come back, I just back off, and then stop. And the driver has two possible responses. She can back off or she can stop. But of course, we have two signaling conventions here. There are two solutions to this signaling problem. So well, the two solutions, we know them. I mean, we can have a convention with this one means back off, and then this one means stop. Or we have the other convention with this one means stop, and this one means come back. Back off. So we model this in this logical system, this logical framework that I've been speaking of, using, again, this same sort of signaling pattern between the quantifiers. For all x, there is a z, there is a y. You can see for all x, for all situations, there is a signal which is sent. And then there is a response y. But of course, the receiver who gives the response, he doesn't see the situation picture. X, the signal has been sent. So, well, the sentence I just repeat what I said before. Z is a signal, R is a response, and the response has to identify the best action. Or you have to have that is a signal, R is a response, and the response actually is to say which state it has been sent from. So we have a signaling system. These are the strategies associated with the two existential pairs, and when there are as many signals as states, then anyway the strategy forms strategy pairs. But then when there are less signals than states, the sentence is indeterminate. That has been very much analyzed by Brian's curves about signaling systems. So, I just given you a few examples of sentences which are very, actually, from a logical point of view, they are very simple. They just involve quantifiers and then identity. And these examples, I mean, the three examples have been for all x there is a y, the matching penny sentence, x is identical to y, then we have this infinity sentence, sentence expressing infinity. And then we have a sentence expressing this kind of Lewis signaling situations. All of them are indeterminate. It just means that they are neither true nor false. And so because they are neither true nor false, we can go on and look for some other solutions for them in game theory. We can actually look at what game theoreticians do to have a solutions to this game. And then, well, they just form what is called the strategic game. And the strategic games are, well, think about this first situation, the magic pen. You have two players, they have to choose up an element, independent of each other, without seeing each other. And for all there is a right where x equals y, in a situation which are just two elements to be chosen, then, well, there are two strategies that theorists can accept. I mean, either she chooses R or she chooses B. And there are two strategies also the universal quantifier has the same, either he chooses A or he chooses B. Then of course the strategy gains, and after coming to the So we look at what is an equilibrium in the game, and we say that a pair of strategies is an equilibrium in the game. None of the players is better off. Again, there are too many mistakes in my presentation. Is none of the players better off by any lateral deviation. And unfortunately, picture is you can't see from that, but I hope that you know when you see the other one that there is no equilibrium. I mean, if none of the players says that, I mean, if a player who withdraws from takeaway, say, this is an equilibrium. I mean, if any of the players will withdraw from this unilaterally, I mean, he will be in a better solution. So this simple game, which is it's a matching game, it doesn't have a solution. But then we have that's how probabilities or mixed strategies comes in. Then we have a probability distribution over the strategies. So the players choose their strategies randomly, as they say. Then we can have a Nash equilibrium. We have an equilibrium, actually. Don't need Nash equilibrium. We have an equilibrium, which is the Nash equilibrium. But, so that's how probabilities come in. And for indeterminate sentences, I mean, for this sentence, the value of the sentence is going to be the expected utility that is returned to the existential plane by the equilibrium in the game, and that's going to be 1 divided by 2. So we go from truth to probabilistic values, and that's what is called, with some of my colleagues, equilibrium semantics. It's a suggestion made by a Hungarian mathematician and also taken by Vlasan Gurevich in '86. So we associate with undecided sentences probabilistic values, and these probabilistic values of the sentences is once again the expected utility, which is given to the existential player by the equilibrium in mixed strategies in the game. Such a mixed strategy always exists and is unique for the class of games I have here. So this is for Neumann's minimum theorem. And with the sentence, apply this example to the sentence defining infinity. We call this sentence, and when a situation is finite, and as I said, we finite know that this sentence is neither true nor false, but now we have this probabilistic values, and this probabilistic value on the model in a situation with n elements is going to be n minus 1 divided by n. It's easy for you to see. I hope that this is why. I mean, how can the existential player, he can identify the value of x n minus 1 times, just like the signal device I showed before, except in one case, which is the value of c. So the value, when the structure approaches infinity, the value of the sentence approaches 1, which is as it should be. One final example, and then I stop. So I'm trying to give you kind of start from evaluation games to evaluate whether the sentence is true or false in a seed situation. Then I have been moving to one of the first questions that I started with is, well, this is just to give an interpretation of the sentence when you know. I mean, the value of the lexical items of the sentence. The question I had was, how do this is going perhaps to show the difference between behavioral methodologies and some other methodologies which have been devised elsewhere and which will probably be, I mean, it will be the topic of some of the talks here. So we have a famous problem which has, for some reason or another, constituted the attention of probabilistic theories, of decision theories and logicians and Bayesian epistemologists, which is called the multi-hole problem. And the multi-hole is hides a prize behind one of the three doors. And then the contestant, who is a lady, C has to guess where it is. And the proper guess is what I said, is door one. Then multi-hole, who knows where the prize, where he has hidden the prize, then multi-hole open the other door, which is empty. I mean, there is no prize behind it. And then he asks the contestant, would you like to change your opinion? Would you like to switch doors? And now the question is, so it's very important. Suppose the contestant C has to guess. Suppose her guess is door one. He asks, well, guess what? Multi-hole asks, where did I put the price? He said, door one. Well, multi-hole from another location of the cell, multi-hole then opens door three. And then multi-hole asks the contestant, would you like to remake your guess? Perhaps, yes, door two. And the question is, will changing to door two improve the contestant's chance of winning the prize? Well, it's very interesting. I mean, I actually didn't find this in the literature. This is a kind of, it has a very good book on probability theory, The Pleasure of Probability, Richard Isaac. Well, he doesn't state it he doesn't state it's a game theoretical problem. It's me who states it like that, because perhaps we see the difference between a decision theoretical problem and the game theoretical problem. And his statement is that he formulated the problem in this way. Multi-hole shows the contestant three doors. Behind one of them there is a prize, so she has, well, you can think this way. Multi-hole has hidden the prize behind one of the three doors. The other two are empty, or sometimes say the other two, there is a goat behind, the other two doesn't have it. So the contestant chooses the door. Multi-hole opens any of the other doors, which is empty. And then she asks the contestant whether she would like to switch the doors and choose the remaining one, which is closed. Is it in the contestant's interest to do so? So what is the difference between the two formulations? And we have another book, Greenstead and Schnell, Introduction to Probability, and then they formulate it actually in this way. They say the contestant can use the stay strategies. I mean, she just sticks to her initial guess, or decline to the cell. Similarly, the contestant can use a switch strategy and say, yes, I switch the doors. And it offers the chance to switch to another face the offer. Now suppose that the contestant decides in advance to play the state strategy, but only action in this case is to pick up the door. What is the probability? So what is the probability that she wins the prize or the car? The same question can be asked about the switch strategy. So we have what I call a distinction between a decision theoretical versus game theoretical formulation that comes up in the literature in these various I interpret them, is not a solution to the original problem. The original problem asks for the conditional probability that C wins if she switches door, given that she has chosen door 1 and Monty Hall has chosen door 3. So we have a kind of, the original problem said, well, suppose that the contestant chooses door 1 and then Monty Hall opens door 3. So now we go for this kind of conditional probability that given the risk set, is it in her interest to switch doors? So, I'll say that the original formulation, which is just this kind of formulation, given that formulation, I expect philosophers to be sensitive to that. In the original formulation, then we have this quotes about conditional probabilities in a particular situation. And then we have a modelization in dynamic logic, epistemic logic, using product models a la alpha and R. And then we have papers by Poirier, Grandi, and Van Benten showing how this can be done. And then we have a game theory formulation, the game theory solution, a modelization in logic. So, once again, I take the moral of this to be that the dynamic epistemic logic approach, has addressed a particular problem of conditional probability, which it's a particular case, given that the contestant has chosen that door, and then given that Monty Hall opens this door, number 3, and what is it in her interest to now switch to door 2? And I take the game theoretical formulation. So that's a general problem. The general problem is better to switch doors than to stay at the initial choice in the general case, or in this game. So a game theoretical solution, and this probably shouldn't be forgotten. The game theoretical solution is not going to give you a particular answer in this particular case. And a solution in terms of conditional probabilities or in dynamic logic is never going to tell you the best response is just switch strategies. Adopt for the contestant, it's rational to adopt the switch strategies. Well, the rest are just details. I'll just take 5 minutes of your time, and well, I'm not very handy. I didn't have time to draw the nice fancy trees with the software I'm using, which is antique. You just imagine that in this original case, where we have a particular choice of Monty Hall and a particular choice of a door by the contestant, a particular choice of a door opened by Monty Hall, then we have a trees where we have Monty Hall can hide the prize behind door 1, door 2, door 3, and then from each of these doors we have again 3 children, because the contestant can guess here, there, and then from each of them, these grandchildren we again, for instance, children we again have 1 or 2 choices, depending on whether the contestant choice happens to be the correct one or not, because the contestant, for instance, chooses a door and then Monty Hall opens the other door. But if, for instance, the prize has been put behind door 1, the contestant has guessed door 1, then Monty Hall can open door 2 or door 3. But this is the only case in which there are 2 cases. And so a maximal branch of these trees has form one, which is X, the door where the prize has been given, Y, the initial guess of the contestant, then Monty Hall opens the door. So now the question is And well, again, probability theories, they think like this. For instance, take the subtree. So this big tree has 12 branches. Take the subtree which represent the event of the price being hidden behind the one. It's like here. For instance, this one, they have the price hidden behind door one, then the contestant guesses door three, then one before she opens the other door, which is two, the only possibility she has. And so there are certain assumptions that are made, and that the game theoretical treatment will not make. And the assumption is, well, the first choice of where multi-hole is going to put the prices are just equiprobable. The probability of each of them is 1/3. The other assumption which is made, well, the choice, the guess which the contestant made is also the equiprobability. You get 1, 2, 3, so they are also equiprobabilities. Each choice also has the probability 1/3. And then when the multi-hole has to choose over one of the two doors, it does it with equal probability, so it will be half. But if she can open only one door, then the probability is 1. And so there's the simple computations. The event of the card being behind the one will be any of this. This is 1 3 multiplied by 1 3 multiplied by 1, which is 1 divided by 9. But in the other cases, I mean, this first two is going to be 1 divided by 8, because I said it's not this opening either door 2 or 3 equiprobable, and therefore it is 1/2. And then we calculate the condition probability. The solution to the original problem. The original problem again being, suppose the contestant chooses door 1 and multi-holes open door 3. These are the events representing that. And then the condition probability will be for her sticking to her initial choice, I mean not to switch to door 2, but C sticking to door 1 is 1 divided by 3, 1/3. While the other condition probability for her going to door 2 is 2 divided by 3. A game theorist, well, a formalization in dynamic logic, as I said, in the kind of models studied by Baltak and Soleski, he may correct me if I'm wrong. It's a very natural one. I mean, you just start with up product models and you have an epistemic model, then there are certain actions opening the doors, and then you move to the next stage, and then another action up, another sort of product, another action, which is so the first action was just the contestant guessing something. The next action, which is the multi-hole opening one of the doors, and then you have probability nicely attached to all of them, and then at some point, in this particular point, you calculate what is the probability that the prize is behind door 2, given that multi-hole has opened door 3, and then you calculate what is the probability that the prize is behind door 1, given that multi-hole has opened door 3, and you compare them and say, well, this is bigger than that, then it's rational for the agent to do that. A game theoretical solutions, which is practically given by sketch by Winston Schnell, is, well, you just work with strategies. I haven't actually seen that in the form I given here, 2-person win-loss game of imperfect information. The contestant tries to identify the door with the prize. Multi-hole tries to deceive her. The representation is richer, of course, because you also have to represent it. Where the prize is, the contestant gets multi-hole provisional, and then do you switch the door or not? And you have, the contestant has one more choice to switch, and it's explicitly represented. And then you have the notion of equilibria that I mentioned before. The strategies in equilibria I'm not going to you form a game, all the strategies, always the switching strategy, the staying strategy, all the strategies are allowed, and then the game is indeterminate, but you go to mixed strategies, you eliminate them, so the game theory procedure is going to, you have to work a little bit to reduce the trees to an equivalent one, and finally, here are the state strategy. Here it doesn't switch it, it switches also. Stick to the initial goals. Here are the state strategies, and you'll see that the state strategies are weakly dominated by the switch strategies. So each of them, for each of them, there is another one here, which weakly dominates it. So it's rational for the player to play those. The game reduces to a simple one, and then the uniform probability distributions for each of these strategies is going to be 2 divided by 3. So, but the important point in the game theoretical solution is not that it's 2 divided by 3. The switch strategy has the value 2 divided by 3. The important point is that the strategy which is the switch strategy dominates the strategy which is the stay strategy, stay behind the same door. And so I have tried to give you a representations of different games and situations in a unified logical framework, which is this logic was dependent and independent quantifiers, in particular independent family logic, and starting with simple situation like matching pennies, where there is no signaling, they're just players, just act independent of each other. The existential player has to identify the choice made by a universal player without seeing it, and of course that's why the games are undetermined. But then I using logic signaling sentences to say that I have logic as this device of signaling where you can insert a dummy element and then that changes everything. And I use this variation of sentence to show you a couple of examples how to formulate signaling games in our logic, how also to formulate multi-hole. This is now it's the first time I'm doing this formula for all x there is a 1. The existential. You can see that the contestant doesn't see it. She has to guess the rule. Then multi-hole again opens the door. And then finally the door is different from the other two. And finally the contestant has another choice, another endeavor to identify the door is the first. And I show you the switch strategies in such a game is the one which is the best, dominates the other strategy, which is the straight strategy, and actually the return payoff to the existential play is 2 divided by 3. And I like to still to say at the end of the talk that, I mean, in these 2 types of situations, in comparison, which I was mentioning short remarks about compositionality at the beginning, the relation between independence logic and dependence logic, the logic developed by Venner, but there are people now doing work on that. Abramsky, unfortunately, was not able to come, has very interesting things to say about dependence logic, and then Gradle and Venner publish papers. There's going to be a nice little conference in a couple of weeks about dependent and independent logics, but there, as I said, there's a difference in the style of representation, which is actually motivated by: do we want to go for traditional logical style reasoning, compositional methods, a la Tarski, which Hodges have extended, or do we want to go for game theory treatment and signaling? And then take advantage of the whole game theory machineries, von Neumann's strategies which are in equilibrium have to have this sort of probabilistic distribution over them. But then the other point I wanted to make in connection with the Monty Hall discussion was that, well, perhaps the limits, or not the limits, the comparison between two different methodologies. I choose the Monty Hall because it illustrates the comparison of two different contemporary methodology of two sort of logical systems. And in my opinion, the dynamic epistemic logic, the dynamic logic brings a solution to a sort of concrete decision-theoretical problem with the knowledge I have in this case, with the updates that I have, the calculated conditional probabilities of this particular choice. The game theoretical solution on the other side is going to give you an answer to the question which strategy is a better one. It's a general problem, and it's going to tell you the switch strategy is better than the state strategies. So I'm sorry for in your sense all the examples that I dealt with actually have been, as you see, have been subsumed under the same logical interpretation, sort of depending on the quantifier, which actually helps you to see signaling. It's sort of unifying thing to all of them. So thank you for your attention. I have to say, these are sort of very tricky and things which are sort of difficult to put on the table and in front of a sort of mixed audience, and it's very difficult to find a balance for what is called the technical solution, the other part, but I hope I managed to give you a slight idea of what is going on. Thank you for your attention.
Thanks a lot. So now we have time for discussion, questions, comments, critique. Any questions? Alexander.
So I found fascinating your this idea of truth values given by the value of the associated game, both for technical reasons but also for philosophical. So it gives you a natural way to model a notion of approximate truth, like a property being approximately true somewhere. And your example with a sentence that defines the infinite models, it's very nice in this respect. So think of a property extensionally as a class of models. On the other hand, if we can express it as a sentence in your dependence logic, would be the class of models for which that sentence has value exactly 1. And now try to generalize this example of the sentence of infinite models to such classes. Like essentially thinking, okay, so the logic gives us a natural notion to say that the property is true enough, approximately enough, by saying the associated value of the game is bigger than 1 minus 1 over n, let's say. What does this tell us about the model itself? Like, how can we see in the model, looking at the structurally at the model, that this is true? So, for instance, in the case of the sentence for infinite models, it's very easy. If the model is big enough in size, then we can see that this is the notion it's captured, like it's really the size. So if it's bigger than n. But for other notions, if you change the class, the property, they will be different. So it's not clear what would be the structural, or if there is a structural characterization that would match this. And that would be very nice to have, also because it will connect very well with other kinds of games, with Ehrenfrost-Frézé games, right? So in Ehrenfrost-Frézé games, the purpose is to see whether two models are similar or not, right? And there it's again 0-1. The game is 0-1. But your approach could give us something more like a continuous number of values, so that you can have two structures being approximately the same up to 1 over n, and that and one would like such a game that matches the one on sentences. So that, for instance, indeed, a model that is, in particular, a model that has size bigger than n, if you play the associated Ehrenfrost-Fessé game, between it and an infinite model, you'll get a truth value close enough to 1. You see, so I think there is a lot of interesting, fascinating technical work that could be done in this frame and relating to the philosophical issue of approximate truth.
Well, yeah, thank you. It's a very interesting question. The connection with the Ehrenfrost games and the I mean, I don't know how to, I don't have an idea to answer, but since you have done your PhD with Barwise, Barwise also has this idea of approximation, but then this is an approximation in a different sense. So we have two kinds of approximation. In this sense that I dealt with is an approximation of the semantic value, the classical truth values by the probabilistic value of the infinity sentence. In the other sentence, the other approximation that Barwise was this first order approximation. I mean, you just replay the game and you approximate the formula, this kind of formula. Well, he expressed it with hanging quantifiers, but you express it with first order approximations. And the first order approximations, of course, are something which are captured by the Ehrenfrost game, the usual one that we have. And so I just interpret your sentence in a way of, your question as a question about what is the relation between these two types of approximation. And yes, well, interesting, fascinating question. Yes, I saw.